notes are about how to graph a logarithmic function. We're just going to go over some methods for how we could get a picture of these log functions. So let's just start with a very basic one. F of x equals log base 2 of x. You might already know what that shape looks like, but in case you don't, let's think about what x values it makes sense to plug in here. I wouldn't really want to start with a number like 0, because you think of log base 2 of 0, that is asking us 2 to what power is 0, and there's no such power, so 0 is actually not in the domain for this function. The first number you might feel like plugging in, I don't know, is maybe 1. 2 to the what power is 1, and that would be 0. So log base 2 of 1 equals 0. You'll need to note that in order to be very successful at graphing these, you want to be very comfortable and familiar with how you evaluate logarithmic expressions. Log base 2 of 1, that should pretty quickly come to you as 0. Another number that's pretty nice to plug in is 2. Log base 2 of 2, 2 to what power is 2? That would be 1. If you try to plug in 3, 2 to what power is 3? I'm not too sure. That's not the nicest number in the world. So my next number that I'm going to choose is 4. 2 to what power is 4? That would be 2. Oh, log base 2 of 4 is 2. Notice what's happening is I'm being smart about the numbers I'm plugging in for our input, for our x value. I'm not just picking any old number. I'm specifically choosing powers of 2, because those will give us really nice outputs. So 8 would be a really nice next number to plug in. Log base 2 of 8 is 3. If you think about values less than 1, but still greater than 0, you might choose 1/2. 2 to the negative 1 is equal to 1/2. Log base 2 of 1/2 equals negative 1. So notice we can get negative values as our outputs. Negative values as our inputs, though, wouldn't make sense. There's no number that we can raise 2 to the power of that will give us a negative output. So you'll notice our domain is, well, we weren't allowed to plug in 0, but we can plug in very small positive numbers, and then we can go kind of as far out as we want. So our domain for this is actually 0 to infinity. Let's plot those points that we have. 1/2, negative 1, 1, 0, 2, 1, 4, 2, and 8, 3. As we get closer and closer to 0, log base 2 of some positive tiny number is going to be a very negative number. Think about 2 to the negative 100 is 1 over 2 to the 100. That's a very, very small positive number. So as we move closer and closer to 0 coming from the right, we're actually getting this behavior. And then we are increasing as we move off to the right-hand side. We're increasing somewhat slowly, but we are increasing. What we've generated is a vertical asymptote. Let me dot that in. So the equation of that asymptote is x equals 0. That's the equation for the vertical line at 0. Notice the range here is unrestricted, negative infinity to infinity. Right? Because we're going very, very negative, and we are we'll get very, very positive if we move very far over to the right. End behavior is something else that's kind of nice to talk about here. And I'm going to write it as x approaches infinity. So as we're going very far over to the right, f of x is also approaching infinity. If you notice, if you're imagining walking along the graph all the way to the right, you will eventually, get as far up as you would like. If we move to the left, though, I can't really say as x approaches negative infinity, because notice, values to the left of 0 aren't in our domain. So our left-hand end behavior is not going to be as x approaches negative infinity, but rather as x approaches 0. And I actually have to say as x approaches 0 from the right, our function f of x is approaching negative infinity. I have to say from the right because there's no graph that exists to the left of 0. So our end behavior is actually a little bit interesting here. I can't say x approaching negative infinity. I can only go to 0, and I can only go to 0 from the right-hand side because there just simply is no graph to the left. We have a restricted domain. So here's our general shape of a logarithmic function, and we can now do all sorts of things to it, make it negative. We can reflect it over the y-axis, over the x-axis. We can, of course, shift it around. We can stretch it. And those are the things that we want to be comfortable with. Let's do one more example of just a shifted log graph. And I want to maybe briefly talk about two different ways of going about this. The first way is by thinking about the parent function. And the parent function is kind of the basic version of the function we have without any shifts. So in this case, our parent function is just log base 3 of x. Notice I switched bases. Our previous example was log base 2. So I'm ignoring that shift, but I do recognize that this graph is telling, or this original function f of x, is telling us a function that's shifted 2 units to the left because of that x plus 2 on the inside, and 4 units down because of that minus 4 on the outside. So my strategy here is going to be graph the parent function and then just shift it 2 units left and 4 units down. Let's see how fast I can graph log base 3 of x. I know log base 3 of 1 is 0, so I have the point 1, 0. I know log base 3 of 3 is 1. I know log base 3 of 9 is 2. And I know log base 3 of a third is negative 1. I like getting one of those negative points in there. So it has the same shape as our other log graph, but because of the log base 3 instead of the log base 2, you'll notice it's not as flattened out a little bit. We had the point 3, 1 instead of the point 2, 1. I'm sorry, it's more flattened out, I guess I should say. We still have that vertical asymptote at x equals 0. But now I'd like to take all of those points and shift them 2 units left and 4 units down. 2 units left and 4 units down. So the point 1, 0 ends up here. The point 3, 1 ends up here. The point 9, 2 ends up here. Again, I'm just taking all those points, moving them. Oh, I moved that one. 3 units left, didn't I? Taking those points and moving them 2 units left and 4 units down. There we go. And of course the asymptote is going to move as well. So if I take that asymptote x equals 0 and move it 2 units left and 4 units down, we end up here. The 4 units down actually didn't affect the asymptote at all, because if you take a vertical line and move it up or down, you're not changing it, but the 2 units left did affect it. So here's our new function. And you might be tempted to erase your parent function because that's not the one you're interested in, but I think it's okay to leave it there. Just make sure you label what your final function is. So I have this nice color coding ability here. I know the blue function is f of x, and that's my final function. And I don't mind leaving that parent function there because it's part of the work that I did to get to the blue function. Another way of thinking about it, if you didn't want to first graph the parent function and then have to shift it, because we did have to graph something twice, is just by making a table. But the danger with jumping right to making a table is, again, you have to be very, very smart about the numbers you plug in. I only want log base 3 of powers of 3. So because of that x plus 2, I just have to be careful about what I'm plugging in. For example, if I try to plug in the number 2, log base 3 of 2 plus 2 is log base 3 of 4, and that wasn't so friendly. Or if I try to plug in 3, I now have log base 3 of 5, which wasn't so friendly. So I just have to work a little bit backwards. I'd like to figure out log base 3 of 1. So what do I have to plug in so that x plus 2 is 1, and that would be a negative 1. Now I have log base 3 of negative 1 plus 2 minus 4, or log base 3 of 1 minus 4. Log base 3 of 1 is 0. 0 minus 4 is negative 4. So I'm doing a lot of that work actually in my head, but we just are trying to choose smart values to plug in for x. The next number I'd like to have after the log is a 3. So what do I have to plug in so that x plus 2 equals 3? And I can plug in 1. Now I have log base 3 of 1 plus 2 minus 4, or log base 3 of 3 minus 4, which is 1 minus 4, which is negative 3. Let's see, to get a 9, I can plug in a 7, and I get log base 3 of 9 minus 4, is 2 minus 4 is negative 2. So I'm generating those 3 points that I plot when I shifted, I'm generating those with the table right away just by plugging in smart x values. So either way works here. If you think you're not so good at the mental math with figuring out what numbers to plug in, then maybe you just want to graph the parent function and shift it. That's fine. Let's just briefly talk about things that happened after we shifted. The domain of our log function is now negative 2 to infinity because of that left-hand shift. Our range actually hasn't changed. It's still negative infinity to infinity. Our asymptote is now a vertical line at negative 2. And we can even say our end behavior is as x approaches infinity. Well, f of x is still approaching infinity. Remember, we're looking at the blue graph here. I'm looking at the blue graph for all this stuff. And now I can say as x approaches negative 2 from the right, f of x approaches negative infinity. So same reasoning as before. We still have no graph to the left of negative 2. So I don't know, by being very comfortable with plugging in values and being comfortable with the shape and structure of log graphs, I think you'll be able to graph any sort of translation or transformation. Good luck.